Uh, can you hear my voice clearly, or should I change my microphone? I realize I don't have my usual microphone here. Can you hear my voice clearly, Trisha?
I can hear it clearly. It's not very loud, but that might just be on my end. I'm not sure.
Okay, how is it now?
Oh, much better. Much better.
Good, 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 good. Excellent. So let me get started. You can see my screen, right?
Yes.
Outstanding. So, welcome again, everybody. Thank you for joining in. And this is the fourth episode. When we talk about India's engineering legacy, most people are surprised. Did we have one? Isn't it the Westerners who have educated us and taught us all these rational ways of doing things? It comes as a surprise to several people when you say, no, we have a long legacy of engineering in ancient India. And astronomy is one such which brings out a killer application for mathematics and those kinds of things which impact our technological world pervasively today. So, today in the fourth episode, I'd like to focus on ancient calendars and also touch on the antiquity of Indian astronomy, which could also be fascinating for some people. So, we'll take a look at some of these things. So, in the first episode, I opened it out with mathematics because, yes, mathematics is a language of engineers. So, what exactly did our ancestors do in math? And we explored and we saw that there's an application driven historical growth of math, enumeration in the Vedas itself with arithmetic, addition, subtraction, in the mathematics of architecture, geometry, right angle triangle, circle, pi, square root, Baudhayana Silpa Sutras, these kinds of works in the mathematics of commerce, in arithmetic, algebra, solving equations, we see in Bakshali manuscript and other such documents. In the mathematics of modeling the celestial bodies, using trigonometry, spherical geometry, approximations, Surya Siddhanta, Aryabhati are examples of these, and very advanced mathematical modeling in function approximation, polynomial series, infinite series, and algebraic geometry, calculus, we find these things in works of Madhava and works of Hemachandra and many others long before even Newton and others came on the scene. So, this is what we covered in our first episode. And we concluded that we can see an amazing journey through time. And we literally saw that over thousands of years, how there's a connected tradition of the growth of mathematics in India. We saw the unparalleled contribution of Indians to mathematics. Nothing like this was there in Babylon, Egypt, or in medieval Europe or elsewhere, Greece. Nothing was there like Indian mathematics. And one should be surprised that this is not acknowledged in Western histories of mathematics, primarily due to their own insecurities, because mathematics and astronomy are seen as a pinnacle of Western accomplishment, right? So India, having accomplished these things, does not fit into their narratives. So that is why we see a neglect of these things. But this is what we saw in our first episode. In the second episode, I wanted to once again emphasize how mathematics and its application is a measure of high civilization and applications of mathematics in architecture and music. We showed how the use of math is pervasive in the Indian civilization, and we saw the application in architecture, temple construction, and the roots of music itself and how it is strongly dependent on mathematics. We saw that. And I also touched upon transmission of Indian knowledge in music to ancient Greece. Then in the third episode, we started exploring astronomy, again an epitome of high civilization. We saw the epistemology that India had a formal way of building up knowledge, and that's called the darshanas. And we saw the roots of Indian astronomy, the Vedas, Brahmanas, Aranyakas, Upanishads, and those kind of early literatures. And we saw observational astronomy wisdom was encoded as stories, as metaphors and stories, Purana stories, and so on. We also saw the phenomena that our ancestors observed and wrote about, eclipses, transits, conjunctions, comets, and more. And we also saw the observed and estimated precision, a very, very fine entity, which we'll talk about more in today's talk also. And through the evidence, we were able to reject many of the Western assertions that claimed that Indians had learned their astronomy from the Babylonians, from the Greeks, and so on. We showed a connected tradition of learning in India, and we rejected several of those assertions. So in today's episode, I want to focus on the second part of astronomy, which is ancient calendars and the antiquity. Astronomy itself, I think I might take one more, if not two more episodes that will go deeper into the measurements, that will go into planetary modeling and those kinds of things in ancient India. So the instances of astronomy, we saw this in the last episode too, are in several Vedic literature, whether it is in Samhitas, Brahmanas, Aranyakas, all the way to Siddhantas. We see astronomy in every category of literature over here. So we need to literally pick and choose from various places depending on what we want to say over here. And we claim that the roots of astronomy go back to very ancient India, where in Jyotisha Shastra, which is the word that Indians use for astronomy, we see the study of cosmology, which is origins, cosmogony on how life came about, earth studies on seasons, ionams, and so on, astrometry, measuring the positions of stars and planets, nakshatras, and so on, planetary studies to study comets, orbits of planets, calendars, which we'll focus on today, astral studies, which is a very small part of Jyotisha, which is predictive of Jyotisha, and the mathematics to model celestial movements, and the tools our ancestors used at various yantras to do these things. And we can have a correspondence with modern astronomy too, what we call modern at least, which is cosmology again, origin of the universe, Big Bang, multiverses and all those kind of things. Astrometry, position of stars, planets through all kinds of mechanisms, we do these things. Planetary science and comets, asteroids and exoplanets around other stars and so on. Stellar astronomy on the life cycle of stars, galactic astronomy, formation, structure, astrophysics, astrobiology, exploration of life elsewhere. And the tools we use today are telescopes, radio telescopes, space telescopes, and so on. And in my lectures, I show how astronomy grew over time in ancient India and was transmitted at various points in time, around 2000 BC to the Fertile Crescent, around 600 BC to the Neo-Babylon, and around 450 to BC to 400 current era to the Greeks and Romans, around 700 current era to the Islamic empires, Abbasid and so on. And so we are seeing from ancient India leading to Siddhantic literature to Aryabhatta to Bhaskara II, the works going to from Brahmagupta's works, Aryabhatta, Bhaskara, going to Islamic countries once again, and from there on to Latin Europe, and Kerala School of Math going on through colonial transmissions to Europe once again. And Europe itself, the aha moment for them is the discovery of the telescope in the 17th century that has sparked what we call modern astronomy, all these things we talked about today. But the roots of that, we can see what a long trajectory we have leading us to where we are today. So the first thing when we talk about calendars is to understand the calendars itself. What kind of celestial calendars were our ancestors keeping track of, and how did they keep track of the passage of time? So we need to understand that they pegged time to the cycles of the moon, to the cycles of the sun, and evidently there was need to have some synchrony between these things too. So I'll quickly focus on this. So some of the basics are what we call sidereal and tropical. I have a little animation over here, which hopefully will start. Yeah. So the sidereal day, if we presume this is the sun and earth is going about its rotation, and by the time it completes 360 degrees, the sidereal day is complete, and that takes 23 hours, 56 minutes and 4 seconds. But then there's a little extra it needs to do to keep up with the sun, right? So this is what gives us a 24-hour day. So we call sidereal day or Nirayana. Nirayana is with respect to some nakshatra in the background, or Sayana with respect to the sun itself, where the sun is, position of the sun. So that is the basic we need to understand over here. Sidereal and tropical. These are two things that we call Nirayana and Sayana. So the time taken by the sun is actually the earth, but from our perspective, it looks like the sun is going around the earth, is defined as a solar year. But then depending on the points of reference, there are different kinds of solar year. So the sidereal one is when the sun comes back to the same nakshatra as we can observe in the background, some nakshatras over there. That is called a solar, a sidereal year or Nirayana year. The tropical is when the sun completes a revolution with respect to the vernal equinox. Some vernal equinox point is there, and that's called Sayana, Sauravarsha, in other words. And there's a difference over there, like I showed in the earlier slide. So the reason, once again, why this happens, because the sidereal day, if we start out a sidereal day, because of Earth's orbit, in 24 hours, it completes approximately 1 degree, right? I mean, it takes 365 days, rounded to 360 days. So it's 1 degree every day, literally. So in that 1 degree, to catch up with the sun, you need some extra movement. That is why you see from 23 hours, 56 minutes, 4 seconds, we are now getting 24 hours for the sign. So again, Nirayana is from selected nakshatra back to that nakshatra. Sayana is from the vernal equinox point back to the vernal equinox point. And there is a key difference between these two things. Now, what are our sources? Because it's all about evidence, right? We can't just talk whatever we want. So Vedanga Jyotishya, which is dated to 1400 BCE, and I'll show you in today's lecture why it is dated to 1400 BCE. It is mostly concerned with Nirayana astronomy, meaning with respect to nakshatras and so on. But then it also contains references to solstices and seasonal awarenesses. This is the Sayana part of it. So both appear to be there, although it is there in Nirayana mostly. Surya Siddhanta clearly has got both Sayana and Nirayana values. Explicit calculations are there for the precession phenomena. I'll talk about that a little later once again, which is about 54 arc seconds a year. Aryabhatta has mostly done Nirayana astronomy with respect to a nakshatra, but is aware of precession, which is called Ayana Chalana. For example, in Aryabhatiya, Golapada 14th verse, we see that. And people who studied Aryabhatta's works and expanded on that, people like Bhaskara the First, Bhaskara the Second, and others, they included seasonal calculations which are clearly Sayana. Then later Siddhantic astronomers like Bhaskara II, Vateshwara and others, they offered both Sayana and Nirayana tables. The Panchanga, it also incorporates Sayana for solar movements and Nirayana for lunar movements. And the importance is there, in applications are there throughout Indian works for ritual precision, for example, or for sign astronomy that aligns with the seasons, and it's ideal for determining agricultural, religious activities, and so on. There is a drift that happens with Nirayana. Nirayana, because it is with respect to a fixed star in the background, it is impacted by precession. Precession is this 26,000 year cycle that the Earth is doing. So the Nirayana calculations can be impacted by that. That is what I try to show here. If the reference frame for Sayana is the tropical zodiac, which is moving with the equinox, whereas the Nirayana, it is a fixed zodiac. And the basis is the equinox point, coming back to the first of Aries, the equinox point, whereas the basis for Nirayana is the nakshatras. And the use case of Sayana is typically used in solar calendars, in some solar festivals like Pongal, like Yugadi and things like that. It is used in Tamil, Bengali calendars. And the Nirayana is mostly planetary positions in nakshatra-based rituals and so on. And like I said, precession is accounted for in the Sayana method, but it is not there in the Nirayana method. So this led to great controversies when the Europeans started studying the Indian astronomy. So Pingree, for example, came with assertions that Indians learned Sayana astronomy from the Greeks. They did not know that. They only knew Nirayana, and also they learned about precession from the Greeks. So this was his assertion. And so we need to talk a little bit about axial precession too. Is that true, what Pingree says? And what is axial precession? I showed this slide in the last lecture too. This cycle of the Earth, where the axis of rotation is tracing this kind of a wobble, it takes around 26,000 years to complete. This is the axial precession. Because of that, the vernal equinox point also appears to be changing with respect to the fixed nakshatra in the background. So that's why it's called precession of equinox. So this is what we are concerned with. And the assertion here is that Indians did not know about this till the Greeks told them. And people like Pingree, who was a professor in universities in New York, he made these assertions in several papers. For example, he's saying it is not unreasonable to suppose the idea of precession was introduced to India by the Greeks, although the parameters chosen by Indians are their own. So he's very uncertain about it. So he uses this kind of twisted language, not unreasonable to suppose the idea of precession introduced to India, but then the parameters are the Indians. And he's pointing out that Vara, Mihira, Lagada, and other people have observed this precession. Well, we can provide a lot of textual evidences to show our knowledge of precession much before the Greeks came into India. And one such is in the Vishnu Purana. In the Vishnu Purana, when Vishnu is talking about Dhruva, Dhruva is the pole star. He's talking about Dhruva and he's saying that a position is assigned to him above all the worlds. And he says, you will reign for a duration of a kalpa. What does that mean? Not only is he saying that you'll be the pole star, but he's saying that you'll only be there temporarily. You will not be there forever. So that shows knowledge that the pole star is going to change with time. That is encoded in a very early text. In the later part of this talk, I'll talk to you about the antiquity of this work. And you can see how ancient some of these statements are. Then we are also seeing, for example, in Vedanga Jyotisha, which we are going to date to 1400 BC, Professor Iyengar is showing that, where there's a statement, if the sun goes north without reaching Stravana or goes south or without reaching Aslesha, it causes great fear. In other words, it is accounting for the fact that because of precession, the position is changing over here. And there is also in Brahmanda Purana, in this chapter and verse, there is a metaphor. The metaphor is a potter's wheel. And the potter's lump of clay moves slowly sitting at the navel. If it is slightly off the center as a potter's wheel is moving, even that is moving very slowly. So it's referring to Dhruva, which is moving in that way. Professor Iyengar is also calling out in this Maitrayani Upanishad. There is a question posed by this king, Brihadrata, to this rishi and asking, why is Dhruva drifting? So clearly there's an observation that the pole star is not fixed in the location as we expected, but it is drifting. That drifting is because of precession. And there is this king who is asking this question. In another place, a north star, understood by us as fixed, has changed its position. So very, very clearly, we are seeing that in ancient works itself, Indians have observed the phenomena of precession. It is not an idea that has come in from the Greeks. In this work, in this journal article on Hipparchus and the precession of equinox, this person is talking about how Ptolemy, who was around 150 current era, he is quoting Hipparchus, saying that the equinox moves backwards by not less than 100th part of a degree per year. Right? This is what he's saying. So the question is, this is why Pingree and others exalt Hipparchus, the Greek, as having discovered the phenomena of precession and exported it to the world, especially India and so on. But then if we take a look at, again, Professor Iyengar's research on the antiquity of Parashara as well as Vrittigarga, he's saying that because Panini, the grammarian, is citing these two scientists, then these astronomers must have lived before the Western date of Panini, 700 BC. So clearly they lived before that. Then we also see in P.V. Kane's work where Vrittigarga, according to him, he said that the Saptarishi would turn from nakshatra to nakshatra, remaining 100 years in each of these constellations. And Professor Abhyankar has brought it out by saying that it is 100 years per nakshatra interpreted as 1 degree in every 100 years, which works out to a precision rate of 36,000 years. So Vrittigarga, who is quoted by Panini, who lived before 700 BC, who said it is approximately 36,000 years for the precession cycle, is being quoted by Hipparchus in 150 BCE. The same figure as Vriddhigarga of 100 years per degree of 36,000 years. And we know that Alexander, he copied Indian texts when he was conquering all these areas near Balochistan. He was copying texts for his teacher Aristotle, and that formed a conduit for India to Greek transmissions. And we know that the library of Aristotle was inherited by Hipparchus. So we know that he had reference to Indian works, and that is how he got to know about it. We see evidence in Surya Siddhanta in addition. Surya Siddhanta says the circle of nakshatras that rotates 600 times in a Chaturyuga, right? It says that it goes first westward 27 degrees, returns back to zero, then it goes eastwards for 26 degrees and comes back to zero. In other words, it's describing a sine wave of this form. And Dr. Raja has decoded this. Others have done that too before him, but I'm quoting Raja here. So the Chaturyuga is 4.32 million years, and the data from Surya Siddhanta says it completes 600 revolutions. So it completes 7,200 years, it completes one revolution according to this. So the Ayana Chalana can be now computed as 600 revolutions into 27 degrees multiplied by 4 segments, 1, 2, 3, 4 segments, multiplied by 60 to convert it to minutes, multiplied by 60 to convert it to seconds, divided by 4.32 million years, we get 54 arc seconds in a year. That is the precision rate as estimated in Surya Siddhanta, 54 arc seconds a year, which is an amazing number. And I also pointed this out in the last lecture, that how Surya Siddhanta, where I'm not going to put a date on it, that shows 54 arc seconds in a year, Vriddhigarga around 36 arc seconds in a year, Hipparchus around 36 arc seconds in a year, which is again quoting the same as Vriddhigarga. In China, Yuxi in 300 current era, 72 arc seconds, Aryabhatta 48 arc seconds, which is better than Surya Siddhanta's estimate. The Arabs, they copied Surya Siddhanta directly, so they are quoting the same number, 54 arc seconds. Then going on to Bhaskara II in 1150 current era, who got a better estimate, 48.6 arc seconds. And they're on to Newton and others who got better and better estimates. But what we're seeing is India clearly has got a connected tradition of learning where these things are very well known. So with that as background, that Indians certainly knew Nirayana as well as Sayana astronomy, which means with respect to a fixed star or with respect to the vernal equinox. Both are known in India, both were developed. Indians certainly knew the concept of precession of equinox, and we got evidence of these things. With that, we go into the calendar itself. And I pointed out these Nirayana aspects, that we had the nakshatra, a division of the sky, in 13 and 1/3 degree segments. So we had 27 of such nakshatras. These are the names of the nakshatras. We also have the lunar months. For example, if the full moon appears over the Vishaka nakshatra, then that month is called the Vaishaka month. Or the month full moon appears Chitra nakshatra, is called the Chaitra Masa. In southern India, it was the Amavasya or the new moon. If the new moon appears implicitly over the Chitra nakshatra, then that is called the Chaitra Masa. That's why we see an offset of 15 days between northern and southern India. And we also have a tracking of the sun as the sun goes from constellation to constellation. So division of the sky was made in 30 degree segments, 12 of them. That is called the Rashi. And this is the various Rashis. And Indians had the concept of Nirayana Meshadi. What that means is the 0 degrees. In the next lecture, I'm going to talk to you about the coordinate systems. Yes, Indians had a coordinate system. Just like you have latitudes, longitudes, alt, easy, and RA declination, Indians too had a coordinate system going back to deep antiquity. The 0 degree was the start of Rashis at Mesha. Mesha's Aries in the English translation. Aries near the Revati Nakshatra. That is the 0 degrees. So very, very clearly, we had all of these to help us to peg calendar to the sky. And we have these solar and lunar months, the Rashis. These are the familiar Mesha, Vrishabha, Mithuna. All these are the solar months. And the lunar months, Chaitra, Vaishaka, and these are the typical lunar months also. Now we can also see the distribution of the nakshatras with the Rashi. This is a familiar Rashi that we have. For example, Capricorn is Makara that straddles these nakshatras, Uttara, Ashada, Shravana, and Dhanishta, a portion of it at least. So this way we are seeing that these 27 nakshatras are distributed among these 12 Rashis that we have. And because of that, we'll have a straddling of nakshatras and so on. And again, to give you a mental picture of what is happening, if this is the earth and the sun, these nakshatras as well as the rashis are these constellations far beyond us, right? So when we are looking towards the sun, this is a nakshatra. It appears that the sun is entering this constellation. The Shankranti means it enters that constellation. So it's Leo because of that. But in our night sky, on the other side, we will see, for example, Aquarius. So anyway, this is the mental picture to have of these things. We have evidence of 5,000 plus years of time constants for the calendar. For example, one muhurta is 48 minutes in our modern measurements. So 30 muhurtas makes one ahoratrams, which is a day and a night, which is a sidereal day. 30 ahoratrams makes one masa, or approximately 30 tithis, 29.5 days. That's a synodic month. 2 masas makes one ritu, or a season of 60 days. 3 ritus makes one ayanam. Ayanam is a word that is used. You'll find Uttarayana and Dakshinayana. These are the apparent movement of the sun. 6 months it appears to go north, Uttarayana. Then we have 6 months toward the south, Dakshinayana. Right? So these are approximated as 180 days over here. And 2 ayanams makes one varsha, or a lunar year of 360 days. Remember, these are all nirayana or sidereal. Now the Rig Veda itself is talking about a year of 360 days, showing you how ancient this calendar is in India. You'll ask the question, what about the remaining 5.24 days? Well, Professor Abhayankar says in very ancient days, this shortfall was adjusted by observing the Atiratra sacrifice. For 4.5 to 6 days, a massive yajna is done, and during that time is not counted. That's how the synchrony was done. Atharva Veda says the rishi called Rohita, he created something called Adhikamasa, which I'll show you presently what Adhikamasa is. He created that. This was an intercalary month that is inserted into the lunar calendar so that we have synchrony between the solar and lunar. Over a period of approximately 3 years, they will average out to the same period. Lunar year and the solar year both be 365.24 days. The Rig Veda also makes allusion to this Adhikamasa. So clearly showing that the mathematics of creating Adhikamasa was also known in Atharva Vedic times itself. We have these things. And we have evidence lasting to the present day. We have evidence of calendars in use in India. For example, we have in northern India, the Purniya Manta, meaning with a full moon, that was the determination of the lunar month. All the ones in blue, northern India, that is how it is used. Then Amanta was the Amavasya, right? So we had in Gujarat, Western Amanta, Southern Amanta, and these were the ones following the Amavasya as a marker of the lunar month. But we also had a solar calendar, and that is there in Kerala, Tamil Nadu, in Orissa, in West Bengal, rather Bengal itself, and other places. We have evidence of this calendar, solar calendar. Why did I say this is amazing? Because in Puranic literature, we find the genealogies of the kings are divided into Chandravamshi and Suryavamshi. The ones who followed the Chandra, the ones who followed the sun. So these are allusions to people who followed the solar calendar and the lunar calendar. And that is why we see even a remnant of that is there even today. So it's amazing to see this. So again, this is the calendar that we have, Amanta, Purni Amanta in southern, western, northern areas. The solar calendar in Malayali, Oriya, Tamil, Bengali, we have these things. And we have various eras. Eras are markers of an epoch itself. And we see various ones over here. So coming to a little math, what's an engineer without some math, right? So let's look at some numbers and all of those kinds of things. So the sidereal and synodic months and synchrony. So we are seeing that one mean sidereal, mean is very important, it's average. One average sidereal solar month, assuming uniformity, right? That's the meaning of the mean over here, is 365.25 days or 30.43 days. This is what we have over here. And we have the civil day of 24 hours is divided into a time measure called Gatikas. Gatikas, 60 Gatikas in a day, or 30 Muhurtas. So each Muhurta is 2 Gatikas. Think of it that way. So this is the periods that we see. I'm not going to read out all these things, but this is the periodicity we see. The solar year's duration and the tropical, the sidereal and the tropical one, or Nirayana and the Sayana ones. So we are also observing that one lunar month comes to approximately 29.53 days. This is the exact duration of the tithis and so on. So if we consider 12 lunar months, 12 times 29.53 comes to 354.36 days. But then we also know the sidereal lunar year, solar year, is 365.25 days. So we have a difference of about 10.8 days. So even empirically we can say, if we insert an intercalary month, every 3 years we can more or less average these things to be about the same. So there is a way in which we insert an intercalary month. If it is a normal lunar year, in every lunar month, there is a solar ingress or a Shankranti. I'm going to show you this picture in the next slide over here. So this is what we expect. When the lunar year month starts, we expect to see the sun entering, or the Shankranti, into a new zodiac. If so, that's a normal year. But sometimes a lunar month falls completely within a solar month. If that happens, there is no entry of sun into the next Rashi. And that lunar month is considered an intercalary month, or Adhika Masa. This picture shows that over here. So this shows the sun entering to different zodiacal signs, into Meena Rashi, that's Meena Shankranti, Mesha Rashi, that is Mesha Shankranti, and so on. So these are the typical solar months that we know. Now, I told you earlier that either the full moon or the new moon will define that lunar month. Let's take, for example, the full moon or whatever. So it starts, or rather the new moon. So the new moon starts over here and starts the Chaitra Masa over here and ends over here. So we see that in between this we have ingress, a solar ingress over here, Mesha Rashi, the Mesha Shankranti. Therefore, this is a normal year. The Vaishaka, again, we are seeing there's a solar Shankranti over here. So for every one of these lunar months, you are seeing that there is an ingress of a solar year. So this is normal. But if you take a look at this one, we are seeing that between the Mesha Shankranti and the Vrishbha Shankranti, we are seeing that there's an entire lunation enclosed within that. There is no Shankranti over here. So this is considered as an Adhika Masa, which is an intercalary month. It takes the name of the next month. So it's called the Adhika Vaishaka, whereas the real Vaishaka month will follow later on. So in this year, there'll be 13 lunar months. So this is the amazing way our ancestors were able to keep track of time so precisely. No other civilization was able to keep time as precisely as our ancestors, thanks to their mathematical prowess and their ability to observe the skies. And what we see over here is Adhika Masa occurs typically after 33 months, and a particular month will become Adhika Masa about every 19 years. And typically we have also found the lunar month of Magha never becomes Adhika Masa. This is because of the particular resonances, the way the solar and the lunar behave, their cycles. In those resonances, we find that Magha will never become Adhika Masa. Adhika Masa typically happens in Falguna and Ashvina months. Now, analogous to having an Adhika Masa, we also have, if in the course of a lunar month, there are 2 Shankrantis, then that lunar month is called a Kshaya Masa, where you delete it. It's a deletory month. It is very rare. It occurs once in 141 years. But sometimes the cycles may come such that it also comes after 19 years or so. And Bhaskara II in Siddhanta Shiromani, he's given amazing formulas with modulo arithmetic and other such things, where he's showing how the Shaya Masa appears in 141 years, or once in a way every 19 years it occurs, or 122 years. Amazing modular arithmetic which is applied to predict when these things will happen. So Shaya Masa occurs typically in Kartika, this Mrigashira or the Pushya, these months, and so on. So we have observed all of these kind of things. So a month where a Shaya Masa is not counted by its name at all, where there is once not counted. A lunar year where there's a Shaya Masa typically will have two Adhika Masas, one preceding it, other succeeding. It's just the nature of what happens over there. So if we have to keep track of all of these things, we note that we have a lunar year, we have a solar year, we also have got something called a Samvatsara cycle, right? It's a calendar. This is a 60-year cycle. Our ancestors had observed that Jupiter, Guru, takes approximately 12 years to come back to the same zodiac, either the Rashi or the Nakshatra. They also observed that Saturn takes approximately 30 years to come back to the same zodiac. So Jupiter and Saturn, the resonance is such that every 60 years, 12 times 5 and 30 times 2, they come back to the same zodiacal plane. Our ancestors observed that and decided to form a calendar based on that. And we have the 60-year cycle based on that. There's a name given to each of these years. So if we have to observe, the lunar year starts with the Chandramana Yugadi, which is basically the Yugadi, at the first day of Chaitra Masa. In southern India, Amanta; northern India, it is Purni Amanta. And the Yugadi falls with this Mesha Rashi, this first of Aries that I talked about. So we have an epoch called Kali Yuga, which I'll talk to you presently, which is approximately 3102 BCE. So if you want to find what is the present Kali year in terms of Kali Yuga, you must take 2025, which is our current year, and add 3101 to it, and you'll get what the current year is. There's another epoch that we observe, which is in 78 current era, called the Shaka year. So if you want to find today's date in Shaka year, you take 2025 and subtract 78, you'll get it. If you want to know the Samvatsara number, you get the remainder after taking 2025 minus 1926 divided by 60, and that remainder will tell us what it is. For example, right now, 2024 to 2025, we are in Krodhi, which is 38. That is over here, Krodhi. This is the Samvatsara cycle we are in. So once again, lunar year starts with the Chaitra Shukla period and ends with Falguna Krishna period, Amavasya. And the solar year begins with Sun entering Mesha Rashi, which is around approximately April 15th in our times. We also have something called Panchanga. Pancha means 5, so there's a 5-part measure of time. And these are typically the Tithi, the Vara, the Nakshatra, the Yoga, and Karana. I'll describe what these things are, but typically the time required by the moon to gain 12 degrees, if you track their longitudes, 12 degrees over the sun, that is called a Tithi. And the time taken by the moon to go 6 degrees ahead of the sun is called Karana, which is half of a Tithi. Now the days of the week are from sunrise to sunrise. That's how Indians observed the days. And it is each part obtained by dividing zodiac into 27 parts of 800 minutes each. Right? This is the arc is 800 minutes each. And the time taken by the moon to cross that part, nakshatra, is approximately about 1 day, 24 hours. And the yoga is a time required for the sum of the longitudes. If you add up the sun and moon, that should increase by 800 minutes. And that is a yoga, basically the angle between sun and moon. So this shows you this Panchanga once again. The basic unit is Muhurta, 1/30th of a day or 48 minutes. The sidereal measurement is Nakshatra. Synodic measurement is the Tithi. Vara is the weekday, Yoga is the angle between sun and moon, and Karana is Tithi by 2. And the day begins at sunrise when these things are determined. And these are all the Tithis that you have, starting from Prathama, Dvitiya, Tritiya, Chaturthi, all the way to Amavasya or Paurnami. So, Again, how do we compute these things? How did our ancestors compute these things? Clearly, they had a calendar. Clearly, they were doing all these measurements and saying festival will start at this time and all these auspicious dates and these kinds of things. How did they do that? So we are seeing that there is something called a dark fortnight and a bright fortnight. So from Amavasya to full moon, the moon is getting brighter and brighter. So it's called Shukla Paksha, that part of the brightening part. From full moon to new moon, the moon is getting dimmer and dimmer. It's called Krishna, or the darker Paksha. That's what it's called. So the Tithi is computed as the longitude of the moon minus the longitude of the sun divided by 12 degrees. And here is an example worked out by Professor Balachandra Rao. In March 21st, 1990, at 5:30 in the morning, this is the sun's longitude. 11 signs, 6 degrees, 23 minutes. And the moon is 8 signs, 22 degrees. So 8 signs means it has crossed 8 rashis. So you take 8 times 30, that gives you 240. And the sun has crossed 11 signs, so 11 times 30, and that gives you 336. 262 and 336 in decimal. So the moon is less than the sun in degrees, so you add 360 degrees to it, and you subtract the sun's longitude divided by 12, we get 23.8. That means 23 Tithis are over, and we are currently running the 24th Tithi. Now, if the Tithi is greater than 15, we only have 15 names, right? If it's greater than 15, that means we are in the Krishna Paksha, meaning that it is going towards the dimming phase of the moon, the dark fortnight. So you subtract 15 from 24 and you get 9. That means the Tithi is Navami. So 9 over here is Navami, right? So this is how our ancestors were able to compute this. This also implies they're able to track the longitude. I will address that in the next talk. In the next talk, I'll talk to you about how Indians are able to compute longitudes and of the heavenly bodies and so on. What about nakshatra? So the extent of each nakshatra, of course, they could see by sight, they knew the nakshatra by name, and they could see where the moon is and so on. So anyway, if the extent is 13 degrees 20 minutes, which is 360 by 27. So if you want to know, you compute the Nirayana longitude of the moon and you divide it by 13 degrees 20 minutes or 13.33 degrees. So this is the formula for that. Once again, a worked out example. On March 21st, 1990 at 5:30 in the morning, the Nirayana longitude is this much. We already worked it out. 262.16 divided by 13 and 1/3, we get 19.66, meaning that 19 nakshatras are over. We are currently in the 20th nakshatra. So the 20th nakshatra in this list is Purva Ashada. We also know the longitude. So we'll actually be able to go out there and say, yes, that's a longitude, that's where it is. So this is the genius of our ancestors, how they're able to do things of this nature. What about yoga? Again, yoga is with this sum of the longitudes of the sun and the moon. Again, on the same day, if you add up their longitudes, you get 598 degrees and it exceeds 360. So you subtract out 360, we get this number, 238 degrees. Converted to minutes, multiplied by 60, you get 14,000 minutes. You divide 14,000 minutes by 800, you get 17.89. So 17 yogas are completed and we are on the 18th one. Again, we have a list of 27 yogas, right? So we know that 17 of them are over and 18th one is this. That is how our ancestors knew what the yoga is at that time. Similarly for Karana, I'm not going to elaborate the point, but we have these formulas, m minus s divided by 6, and that gives you the Karana. Now, the Westerners hated all of these things. So they said Indians didn't have the concept of Tithi because Tithi is synodic. They only had sidereal. The synodic is a problem for them. So they said this whole notion of Tithi has come from Babylon into India. That is what Pingree the Great asserted this in this paper on astronomy and astrology in India and Iran. He says that the use of Tithi, he's saying it also played a role in Babylonian linear astronomy. It seems likely, again look at the uncertain language in a research paper. It seems likely that Indians borrowed the concept from Mesopotamia, although the exact origin of Tithi is obscure. He still doesn't want to attribute this to India. That is the bottom line. because there are some assumptions they are made and they have to stick to those assumptions. So they try to discredit the data. That's what's going on over here. Bill Mark, who's another researcher, he's done a lot of research in astral studies, and this paper he wrote in 2013 in the Journal of Indian and Buddhist Studies. So he's talking about a work called Tithi Karmaguna in Gargiya Jyotisha. So he says that Indians had the concept of a Tithi long back. Evidence of that continues to exist in Buddhist literature. This was forgotten. It became obsolete by the time of Varahamira. Indians were no longer using that particular mechanism, and again some other mechanism comes. So he's saying that's completely not true, and he's showing this is the table in Buddhist sources. These are the names, 15 tithis, and these are the names of these tithis. So he's showing how Indians had this. These are the deities associated with each of these tithis. And this is preserved in the Buddhist literature that is there in China, Tibet, and other places. And so Tithi is certainly not a borrowed concept from Mesopotamia. Rather, Mesopotamia seems to have got it from India. That is the implication over here. What about the weekdays? So we are seeing that these are the weekdays. We have Ravi, we can say Vara, Somavara, Mangalavara, all of these things, which is the Sun, Moon, Mars, Mercury, Jupiter, Venus, Saturn. There's controversy till the present day with many Eurocentric people asserting that the days of the week and other things came from Europe into India. It is not an Indian invention. But then we are seeing that in Aryabhatiya itself, we are seeing a particular ordering of the weekdays. We are seeing in Surya Siddhanta, in this particular verse and chapter, we are seeing how the days of the week were even named. And there are ways to compute this. I don't want to go into that depth over here. But the way it is arranged is in descending order that you see of the orbital period. Shani, Saturn is the slowest, 29.5 years. So it's right at the top. And the moon at 27 days is the fastest, so it is over here. Then there's a certain way of computing the hours of the day from 1 up to 24 hours, then going on to the next one. So from Saturday, it becomes Sunday over here, then goes to moon and becomes Monday over here, and so on. This is one suggestion, this is only a model. Then we have evidence in Surya Siddhanta itself. If you take a look at Surya Siddhanta, it gives a lot of data. I'm going to explain this in greater detail in the next lecture, where I'm going to show you the planetary modeling that Indians did. In this planetary modeling, the data comes from Surya Siddhanta, where it's saying in a Chaturyuga, how many revolutions of the sun are there? How many revolutions of the moon? 57 million, for example. How many of Mars? 2 million, 200 and so on. Of Mercury, how many? There is 17 million. Of Jupiter, 34,000. Of Venus, of Saturn. So we are seeing the ordering is Sun is first, Moon is second, Mars is third. We are seeing Mercury is fourth, Jupiter is 5, Venus is 6, Saturn is 7. So implicitly, even the way in which the data has been described in Surya Siddhanta follows the ordering of the days of the week. So it's highly unlikely that even the days of the week is a European import into India or a Babylonian import and so on. We seem to have evidence over here that we have such things. Then we have several eras. Eras mark the passage of time. How many years have elapsed since a certain kind of an event? We have the Kali Yuga, which I'll talk about today, which in the Gregorian calendar is 3102 BCE, or Buddha Nirvana, or other Shaka era. Also another, according to Vedavira, there are two Shaka eras. One Shaka era, other than the Shalivahana, which is 78 current era, which we are confusing with Shaka. Anyway, it's clear that we have got enormous time cycles if you look at the kind of time that Indians have been tracking. Even today, when devout Hindus do the Sankalpa, they refer to the amount of time that has passed from Kali Yuga onwards. So it's a cultural memory that is there in our civilization for such a long period of time. Then we also seem to have had periods of times that are called yugas. So we have got a 5-year yuga that seems to have been in the Rigveda Samhita itself, that is talking about 5-year yuga, as well as in Vedanga Jyotisha, that is talking about a 5 years that make one yuga in Vedanga Jyotisha in verse 28, for example. It's talking about that. So at a very early period of time, we seem to have had this 5-year yuga. But we also had other definitions of yuga. For example, we had a definition of yuga which is in terms of divine years. There is a dawn, then there's a golden age, the Krita Yuga, as well as the twilight, Sandhi, basically. 400 years, 4,000 years, 400 years, amounting to 4,800 years. Then we have the Silver Age or the Treta Yuga, which is around 3,600 years. Then we have the Dwapara Yuga, which is 2,400 years, and the Kali Yuga, which is around 1,200 years. If you add all of these things, it comes to 12,000 years, right? And this is there in the earliest literature in India. Then we are also seeing the Puranic literature, this multiplier came in. One divine year is 360 human years. And through that, we have got now the duration of a Chatur Yuga is 4.32 million years, thanks to this kind of a multiplier effect. Then we are also seeing that Aryabhatta, he also considered that the Mahayuga is 4.32 million years, but he took each yuga to be equal in length. Each was 1.08 million years. But then other astronomers took a ratio of 4:3:2:1. So basically saying that if Kali Yuga at 432,000 years is 1, multiply that by 2, you get this Dwapara Yuga. Multiply this by 3, you get the Treta Yuga. Multiply this by 4, you get the Satya Yuga. So this is the timelines that are described in Surya Siddhanta, for example. Then we have concepts like Manvantara. For example, over here we have that, where is this? Yes, so the Manvantara is 71 Chaturyugas. If you take 71 Chaturyugas, it makes one Manvantara of this duration. If you take 14 Manvantaras, it forms one Kalpa, which is 4.32 billion years, approximately called as the day of Brahma or the night of Brahma. This is the kind of timeline. So our ancestors were developing these huge timelines for the purpose, I presume, for accuracy in astronomy calculations. We will talk more about this in the next episode, but it is intriguing to see these very, very big numbers coming in over here. Now, when we're talking about calendars, everything I talk to you now is based on uniform ideas. Engineers are very aware of these things, that we have something called uniformity, and the real world in non-idealness, we don't have uniformity at all, right? Uniformness is the first assumptions, the first approximation we make to get a handle on difficult, complex problems. But what we're seeing is that we have very, very non-ideal calendar elements, and I talked to you about that. One such thing is there in something called the Drik Panchanga. What does Drik Panchanga means? Drik means direct sight. So when you go out at night and see the sky and observe the celestial body position, that is got by actual observations and not by uniform calculations. So when we do a Drik Panchanga, we are seeing things like this. For example, in this calendar in May 2024, when I made this, between 5th and 6th, if you look at the Tithi, it is jumping over here from Dwadashi to Chaturdashi. So if you look at this table I put over here, Dwadashi is the 12th one, 13th one is Trayodashi, 14th one is Chaturdashi. So where did the 13th one go to? It jumped one over here. Similarly over here, you see Trayodashi, here also Trayodashi is repeated twice. We are seeing things like this. I hinted to you earlier about this intercalary months, but why are they happening over here? What are the reasons? And we are seeing such things in other months. So why is the computed Tithi off by 1 day sometimes? Well, there could be several reasons. Maybe the methodology of computation of the apparent motion of moon is taken very uniformly, simply, or maybe if you do it in more complex ways, you'll get all these issues. There are variations of lunar motion. We can look at that. I'll talk about that the next slide. Or calendar adjustments. We talked about the intercalary days. Observational versus calculated Tithi. Because of all these reasons, we speculate it might be different. Now we'll go a little deeper into that. This is a physics primer. We have studied in high school that you take a pendulum and you swing it. What you see is the velocity goes to zero at the maximal point when the potential energy is highest and the kinetic energy is zero. Then when it swings down, the kinetic energy is maximum here, potential is zero, then goes back to velocity equal to zero over here. So here it's Earth's gravity, basically it's concentrated in the center of the Earth, and that's pulling this object towards it. So you have maximum velocity when it comes closest to the Earth in that sense. So if we can take this analogy to the orbital periods, which we'll discuss in greater detail in the next episode, but if you take this as the sun, and if you take this as the Earth, what we see is when the Earth comes, the orbit is elliptical, it is not circular. So that's the first non-ideality. The orbit is elliptical. When it comes closest to the sun, it's perihelion, and when it goes furthest away from the sun, it is aphelion. So the Earth speeds up as it comes closest to the sun, and it slows down as it goes further away from the sun. In other words, in time basis, the rashis will not be uniform. That's the first thing to keep in mind. And similarly, if this is the Earth and this is the moon also does something similar. As it comes closer to the Earth, it speeds up. As it goes further away from the Earth, it slows down. So we are seeing these. We know from physics, this is what is happening. Now we are seeing that our ancestors have done some non-ideal calculations that leads me to believe that they've accounted for elliptical orbits. Even if they did not express it explicitly, indirectly it has been accounted for. In the next few slides, I'll show you these things. Before I go there, I need to talk to you about the moon. The moon is not merely going around the Earth. It has got additional movements, right? Additional degrees of freedom. And one of them is called lunar A, standing for apogees cycle. Other one is lunar N, standing for ascending node cycle. Now, our great astronomers like Aryabhatta have noticed these things, and they have said how many revolutions of the apogee, right, is there in a Mahayuga? 488,219. How many of this ascending node? This many numbers, which in a number of days is 3,231 days or 6,794 days. I put this table for a different lecture to compare it with Ptolemy. Ptolemy has also done these things in the modern numbers to show that if somebody accuses Aryabhatta of copying from Ptolemy, the question is, why are there differences? Why are they not exact? For example, this lunar N, Ptolemy said 6,796 days, but Aryabhatta 6,794 days. The modern is 6,793. Aryabhatta is even more accurate. Every one of these numbers is a difference between Ptolemy and Aryabhatta. This belies the accusation that Aryabhatta is copied from Ptolemy. That simply cannot be true given these kind of things. But we are interested in knowing what is this lunar A and lunar N. Well, this first one, this lunar A, it is an orbital period of apogee of the moon. Apogee is when it goes furthest away from the Earth, right? Look at this picture over here. If this is the Earth, the apogee is over here. Now, it is not merely doing this forever and ever. Even the point where the apogee happens is cycling. It is going around the Earth. This is what you should keep in mind. Whereas this egg-shaped thing, this is also cycling through the Earth, as you can see. And this cycle takes approximately 8.85 days, or if you multiply by 365.24, you get 3,232 days. So this is what Aryabhatta had called out. Our ancestors had observed this. They observed it, measured it, and said this is what the time period for this moon's apogee movement is. Similarly, the ascending node. This ascending node is basically, it is a point where the moon's orbit crosses the ecliptic. Ecliptic is the path of the sun. If you remember, I told you there's a 5-degree offset between the ecliptic and the moon's orbit. So where they intersect, that is called the nodal points. Those nodal points are also precessing, and this precession takes approximately 19 years or 18.6 years to complete. So 18.6 times 365, you get 6,792 days approximately. This is what Aryabhatta had pointed out. What do these things mean for us? These things mean that there are some non-idealities in the behavior of the moon as observed by us. So if I have a uniform calculation, the mean calculation saying everything is 30-degree segments, 13 and 1/3 degree nakshatra separation, those things are not true because of these kinds of things. So we have to now show evidence that Indians had time measures and they were able to have measurements of time. So these are the kind of measures we had. This is from this book, Indian Calendar by Dikshit and Sival, written around 1860 or 1870. So we had something called Prativipala, which is in our equivalent 0.006 seconds. Yes, we were measuring those kinds of things. 60 of them makes one Vipala, 0.4 second. 60 Vipalas makes one Pala, 24 seconds. 60 Palas is 24 minutes, half a Muhurta. 60 Gatikas makes one solar day. So this is the kind of time measures that we had. We had water clocks and other such things. Maybe in the 4th episode of astronomy, I'll call the measurements that Indians did, what instruments they use for these things. So with those kind of measurements, Indians were able to measure the durations of these things. We are seeing the non-uniformity of Tithi. We said Tithi is, the 12-degree separation, but then we know separation is not going to happen uniformly. We presumed uniformity in 29.5 days for a complete Tithi cycle, but that is not true, right? It is a time occupied by the moon in increasing distance from the sun by 12 degrees. Because the motions of the sun and moon are always varying in speed, the length of Tithi is constantly changing. So the average in Gatikas, Palas and Vipala is this much, or in hours, minutes and seconds, it is this much. So the greatest length is 26 hours, 6 minutes, 24 seconds, and the least length is 21 hours, 34 minutes, 24 seconds. So what are you seeing here? Our ancestors were not fools. They observed all of these things. They knew the non-idealities. They started out with the ideal, but they knew the non-idealities. They were able to map out these things. They were able to get the measures, observations to fit all of these things. Implicitly, we have fit this ecliptic path, orbital paths by doing things of this nature. Non-uniform size of months, even the length of the month, right? We said that the lunar month is always a certain amount, or the solar month is always 30 days and so on. But in terms of two texts, one is the Arya Siddhanta, other is the Surya Siddhanta, in days, Gatikas and Palas, or in days, hours, minutes and seconds, we are seeing the different months, Mesha, Vrishabha and all these are the different months. We are seeing the duration is changing. 30 days or 30 days, 22 hours. 31 days, 9 hours, all the way to 29 days, 21 hours, and 29 days, 8 hours. So what are we seeing? Indians have estimated which are the months where the earth seems to be speeding up, which are the months where the earth is going slower, because that will control the apparent movement of the sun from one zodiac to the next. So clearly they have measured these things, and we have evidence in our ancient texts that these things have been used. The person who wrote this, Dikshit, he says, my opinion is these things were used in India 700 BC to 300 BC. I think I should skip this. We have something called Adhika Akshaya Tithi also, because remember I said that 12 lunar months is 354 solar days, right? But then we are saying there are 360 tithis. So that means 6 tithis must be expunged, they must be removed out. So there are formulas to do that, and those are the Adhika and Kshaya tithis. Now, non-uniformity in nakshatra and yoga duration too. Even this has been observed. Although we said nakshatras are divided into 13 and 1/3 degree segments, this is not true. The moon's path through the nakshatras is not uniform. And the greatest, the mean is 24 hours, 17 minutes. Greatest is 26 hours, 32 minutes. The least is 22 hours, 22 minutes. Similarly, the yoga also, because of that, it's a difference between the longitude of sun and moon. This will also change over the duration of the year, and that is what our ancestors have measured over here. The length of the year, even that, as you can see, depending on the work that we have, Vedanga Jyotisha, Paita Mahasiddhanta, Romaka Siddhanta, Pulisa Siddhanta, going all the way to later works, we are seeing that whether it's in Gatika, Palas, Vipala, and others, or hours, minutes, and seconds, and days, we are seeing that the duration of the year is changing, right? In other words, not changing, but the estimate is getting refined, is getting better and better. The modern measure is 365 days, 6 hours, 9 minutes, 10 seconds. And our ancestors had got it down from 365 days, 8 minutes in the Paitama Siddhanta, to 5 minutes by the Romaka Siddhanta, to 6 minutes in the Surya Siddhanta, and going down to 6 minutes, 12 seconds by the year 1042. We had got this kind of measure. Again, giving you an idea of the kind of accuracy ancestors were able to do. And if you take a look at the length of the year, we are seeing that the solar month, 1/12 of the sidereal year, Surya Siddhanta is 30.438 and modern science 30.438, as you can see. In the lunar month, it's up to this 1, 2, 3, 4, 5 decimal places we can compute it. So in other words, the accuracy, it's again highlighting the kind of things our ancestors are able to do. And you must ask the question, what measuring instruments did they use to achieve this kind of accuracy? We'll try to address that in a later episode. I'll skip this equation of time. And the non-uniformity of nakshatras. Like I said, we have accepted that the length of the nakshatra division is 800 minutes, right? But then we have evidence that Brahmagupta and Bhaskaracharya, they are referring to a system by Garga, where he's saying that there were different lengths for the nakshatras. 6 nakshatras had half the normal length, and 6 of them had 1.5 the length, and remaining 15 had the normal length. So we take a look at Garga system, and we take a look at Brahma Siddhanta system. We are seeing that. In uniform terms, everything is 13 degrees, 20 minutes. So keep adding them, multiplying them, and you get this 360 degrees by 27 nakshatras. But then here you see it is not the same. It's not a simple multiplier. These are non-uniform. So clearly, we have had attempts by ancient Indians to try to make sense out of these things. Okay, so what I've done so far is I've talked to you about calendar systems, gave you a brief overview of many of these things. I'll quickly talk to you about the antiquity seen in Indian astronomy, because this is also pretty important. And the most important thing, once again, for us is axial precision, because our ancestors have left observations of when did the equinox or the solstice happen in sidereal terms, which means with respect to a nakshatra, when did a certain event happen? Now, because of precision, that sidereal measurement will no longer be valid because the earth is precessing over thousands of years, it changes. But because we know precision rate, we can work backwards in time and tell you when was that particular observation made. This is called archaeoastronomy. This is what we're going to use now. So the first thing is, what is the antiquity of a book? This Vedanga Jyotisha written by Lagada. Several people tried to make stabs at the date. Weber 500 BC, William Jones 1181 BC, Tilak in this time frame. Colebrook came close 1381 BC. Dikshit came the closest with 1400 BCE. And how we figure out the date is, inside the Vedanga Jyotisha, there is a verse, 6th verse, that says, winter solstice occurred when the sun and moon came together in the Dhanishta nakshatra, which is Beta Delphini. So we got to figure out when in the past was winter solstice at Dhanishta nakshatra. I have already done these things in the planetarium software. I've used Stellarium to do this simulation. So what you're seeing here is a projection of Earth's latitudes and longitudes in the sky, where they become celestial coordinates. For example, this here is a celestial North Pole. On Earth is a North Pole, in the sky is a celestial North Pole. These circles are the latitudes on Earth. In the sky, they become declination. And these lines here are the longitudes on Earth. In the sky, they become RA, or right ascension in the modern terms. And this line that you're seeing is horizon, or the ground line. This is the west, this is east, north, and south is towards us. Think of a 3-dimensional plot over here. And given this, if we take a look at this as 90 degrees, because the celestial North Pole, and we count 90, 80, 70, 60, 50, 40, 30, 20, 10, 0. 0 is very special, right? It is the equator. On Earth, 0 degrees is the equator. In the sky, it's a celestial equator. This is minus 10, approximately minus 24. So when the sun has gone south to minus 24, it is winter solstice in northern hemisphere. When that happens, along the longitude, we see the nakshatras Dhanishta. This is the star, Dhanishta, Beta Delphini. And this, to do this, I had to crank this back to 1440 BCE, right? Approximately 3,400 years before present. I had to crank the time back in order to observe the sun winter solstice occurring in Dhanishta Nakshatra. So this is the date of Vedanga Jyotisha because of the artifact it contains within it that tells that this is when this happened. Now, I pointed out to you the story of Dhruva, right? So Vishnu says Dhruva will be made into a pole star in the sky, where his position will be so high in the sky. And he also says that all the other stars and the Saptarishis will go in pradakshina around you. In other words, an assertion that Dhruva is immobile in the sky. Vishnu also says your mother Sumati will be near you. That is an archaeoastronomical artifact. And that is telling us that Sumati has got to be close to him. Now, I'd like to show you this on the planetarium software. So bear with me when I get this over here. This is the planetarium software, and I'm going to play with the dates over here. So right now, it is the current date, which is 2025, January 1st over here. And what you observe is we have Polaris, right? We have a pole star here, Polaris. But we don't find a companion to Polaris. So the question comes, was Vishnu Purana talking nonsense? Because it says, Dhruva, you'll be the pole star and your mother will be next to you. Where is his mother? We can't see that over here. So some people say Vishnu Purana, people like Wendy Doniger and others say Puranas were written in the Gupta time frame around 500 current era. So let me put the year to 500, year 500. So I changed this date to 500. Now this 500 current era. And what you see is there is no pole star. This is the precession circle. And what we call Dhruva is yet to come here. This is Dhruva. And there's no pole star. So how could Indians have written the Vishnu Purana in 500 current era talking about Dhruva being the pole star if there's no pole star, right? How will they do that? Let us go to the year 0, the turn of the common era. If I go to 0, once again there's no pole star. What about earlier than that? If I go to minus 500, which is 500 BCE. If I go to 500 BCE, there is no pole star over here. If I go to 1000 BCE, I don't see a pole star here. If I go to 2000 BCE, there is no pole star over here. But if I go to 2800 BCE, yes, I do see a pole star over here. And I see a companion. I see a pole star, I see a companion. You should be amazed. Vishnu Purana contains this particular innocent looking statement saying, Dhruva, you'll be the pole star, your mother will be next to you. There is no period of time in Indian history or world history when there would have been a pole star with a companion next to it, except in 2800 BC, like I've simulated over here. Okay, let me go back to my presentation over here. So that is what I've shown over here. In our time, Dhruva is a pole star, there's no companion. But if you go back to 2800 BCE, we see Thuban, that was a pole star. So in the time when these works were written or composed, Thuban was a pole star, not this. This was Dhruva at that time, and there's a companion next to it. We have a work called Shatapatha Brahmana, written by Rishi Yajnavalkya. So Yajnavalkya was trying to tell the Vedic practitioner how to identify the east direction. It's not a trivial question because Indians are aware of Ayana, right? Uttarayana, Dakshinayana, where the sun goes to northernmost point, southernmost point. So they knew that east is not where the sun rises because it keeps changing over a span of 46 degrees. The sun is going around in a year. So he says the true east is under Kritika Nakshatra. So we are looking for a point where Kritika is on the vernal equinox point. When it's the vernal equinox point, Kritika will be on the celestial equator. When Kritika is the celestial equator, that's a true east direction. That's what he's saying. It does not move away from the eastern quarter, Kritika. Therefore, you can light your fire under that. So to simulate this, I had to go to 2982 BCE. Once again over here, if you start counting, so if this is 90, 80, 70, 60, 50, 40, 30, 20, 10, 0. 0 is the celestial equator. This is the horizon line. So this is night on this side and day on this side. The sun is still below the horizon. So early in the morning, when the Vedic practitioner arises, has a ritual bath, still dark, you can see Kritika in the eastern horizon. Then 1 hour later, the sun rises, washes out Kritika, but you got 2 points. Kritika was there, sun is over there, draw a straight line, put your bricks over here, start your Yajna Homam over here. So this is how Indians were finding the east direction, for example. And to identify this, Kritika on the equinox, we had to go to 2982 BC, approximately 3000 BCE. Then there's an ancient epoch in our tables. Puranas talk about Kali Yuga. Aryabhatta, Surya Siddhanta referred to it. Pulisa Siddhanta, Brahmagupta, even Al-Biruni is talking about it. Temple epigraphy in Karnataka, Aihole, that refers to this. Cassini, who was an Italian astronomer, he got tables from Thailand called Siam tables, astronomy tables, and he studied them, and he said it has got the longitude of Ujjain in it. It's also got a calendar system with an absolute date of 3102 BCE, February 18th. This is what Cassini said. And later, Playfair, Bentley, Colebrook, Burgess, they all studied the same phenomena in Surya Siddhanta and confirmed this date. It turns out to be a conjunction of planets, all the planets, Sun and Moon and Revati Nakshatra, which we are observing as Kali Yuga. Again, I simulated that. If we go to February 18, 3102 BCE, the Sun is over here, right at Revati Nakshatra, Chandra, the Moon, Guru and Shukran, Jupiter and Venus, almost on top of each other over here, Mangala, Mars, Buddha, Mercury, and Shani, Saturn, little outside, but more or less clustered. Now, this is a planetarium software based upon a lot of polynomial approximations. We don't know the accuracy as you go further back in time. So we don't know whether this is tighter clustering or whether this is in reality what it was. But at any rate, our ancestors assumed this is a 0 point. Everything was clustered over here. So in the next episode, I'll talk to you about this, how it formed the coordinate system for Indians. Then we have got something in our text referencing Aditi. Aditi is, directly go to this. In the Aitreya Brahmana of the Rig Veda, this is a translation by Martin Hogg, it talks about the yajna, the sacrifice, going away from the devas. The devas are unable to perform any ceremony. They did not know where it had gone to. They said to Aditi, let us know the sacrifice through thee. Aditi said, Tatastu, let it be so, but I'll choose a boon from you. They said, choose. She said, all yajnas will begin with me and end with me. This cryptic passage over here refers to the fact that our ancestors had a celestial calendar. And over 1,000 years' time, that celestial calendar has changed because of precision, right? Because of that, they don't know when to do their auspicious things like festivals or occurrences or yajnas. They don't know because they're following the celestial calendar. So they're confused. So they have reset the calendar to Aditi. And Aditi is saying, the new year will begin with me and end with me. Vernal equinox is the new year in India. Vernal equinox begins with me and ends with me. That is what she's saying. So this is a metaphor for the change in calendar system from an earlier calendar era. They have reset the calendar to Aditi to account for the impact of precision. That evidence is clearly coming out. So we have to answer some questions now. What is Aditi in our nakshatra model? Question number 1. Question number 2. When was it on the vernal equinox? Well, Aditi turns out to be part of the Punarvashu nakshatra. Punarvashu nakshatra has got 2 stars, Diti and Aditi. In the Greek tradition, it's called Castor and Pollux. Castor and Pollux are Diti and Aditi. And to simulate them being on the vernal equinox point, I had to go back to staggering 6000 BCE. If you go back to 6000 BCE, we are seeing that sun is at this point, equinox point, and in the longitude you got Punarvashu. Now some of you may feel very uncomfortable with dates like this. So it's not very surprising if you consider the latest archaeological finds in Birana. In Birana, radiocarbon dating now has shown Saraswati Sindhu artifacts going back to 7500 BCE and earlier, some of the earliest artifacts, which is 9000 years before present. So we should not be surprised that our civilization, we have been observing the stars for a long period of time and having calendars. It does not take great genius to do these things. It only calls for logical, rational minds to do these things. So this is not so strange. It is strange if we accept Aryan invasion, if we accept that Aryans came to India in 1500 BC as tourists or migrants or invaders. If we accept that, then all of Vedic systems must be after 1500 BC. None of this makes sense. But if you reject the Aryan invasion nonsense, then suddenly all these artifacts we have in our text can be reconciled. Reconciliation in data is critical to engineers, right? So if you have a model, we want to reconcile that to data. We want to correspondences over there. We can do that if we get rid of this Aryan invasion nonsense. We can reconcile all our data with radiocarbon datings and other things. We have Surya Siddhanta talking about the conjunction Mesha Rashi that comes to February 22nd, 6779 BCE. Incidentally, this was also talked about by Megasthenes in his work called Indica 300 BCE when he came to Magadha. He's talking about Indians having a king list going back to this period of time. Then we have, I'll end with this. This is the last point. I'll end with this. This is fascinating for me because this is a rare case where we have scientific validation of a date that I'm going to propose to you. So we have the story of Surya in the Rig Veda where Surya becomes so hot. He becomes so super hot that his spouse, Sanjana, could not take the heat. She abandons her husband. She leaves a shadow Chaya in her place, abandons her husband, goes off to the cooler region. One fine day, Surya discovers a deception and he asks this Chaya, who's a person that Sanjana has left behind, and he asks, where is my wife? And she says, she's gone to the cooler region. Surya goes to the cooler region and he finds that she's taken the form of a horse. He too takes the form of a horse, and the Ashwini Kumaras are born in that union. These are the Ashwini Kumaras. Associated with the horse, we find them in Mitanni culture, in the Hittite culture, in so many world cultures, we find these twins, right? We'll talk about that perhaps in a later episode. But at any rate, we find this Rig Vedic verse over here, Ushas. Ushas is the goddess of dawn. She heralds the sun. So it is saying, Ushas, awaken the Ashwins for their share of the Vedic sacrifice. So you're awakening babies, right? Not adults. So she's saying, awaken the twins for the share of the Vedic sacrifice. What does it tell us? That sun has gone to the cooler region, implying it's winter solstice in the northern hemisphere. And in the northern hemisphere, Ashwins are appearing with the sun at dawn, heliacal rising. So if we go and track this date, this came to 7,200 BCE. At this point, 90, 80, 70, 60, 50, 40, 30, 20, 10, 0. Minus 10, minus 20, minus 24. When the sun is at a winter solstice point, in this longitude, we have Ashwins over here. So this came to 7,200 BCE. So again, the question is, what on earth? This was called out by Balagangadhar Tilak about 100 years ago. Then Abhyankar about 40 to 50 years ago. I have been popularizing this from the last at least 2010 or so. In my talks, I've been talking about this particular episode. Imagine my shock when this paper came out. This paper came in Nature, which is a very reputed journal, in 2022, where these researchers talked about an extreme particle solar storm in 9125 years before present, exactly in 7176 BCE. I derived this date purely on the data given in the Rig Veda, right? That we said winter solstice, Ashwins, we work it back in the stellarium, and we got this data 7,200 BC, plus and minus 80 years, this side and that side. And these people came with a precise date, 7176 BCE, when there was this energetic storm. It is not an ordinary storm. There's a second paper that came out in 2022 that's talking about tree rings that is revealing a proton event in 7176 BC, and one more later on. Now, what is this referring to? We know that from science, we know that the sun goes through a sunspot cycle in 11 years or so. It goes to maximum, minimum cycle. We are going towards the maximum right now. So during these sunspot cycles, what happens is there's a whole lot of stellar things to think about over here. Magnetic activity, cooling regions in the sun, and other such things. Eventually, what happens is there are different atmospheric bands on the sun that rotate at different speeds. And there's magnetic lines of flux that connect these various sunspots and other such things. Time to time, what happens is that the magnetic lines snap. When they snap, they're stretched like rubber bands, literally. And when they snap, that energy sometimes throws out particle matter. We are not talking about photons here. We're talking about protons over here, right? Actual particulate matter is ejected from the sun. It's called coronal mass ejection. And this is one such example of coronal mass ejection being thrown out of the sun. And we are interested in this because if this particle storm reaches the Earth, there are some consequences for us. What happens is these are charged particles. In Earth, we got our magnetic lines of force. So when these particles come towards the Earth, our magnetic lines, they conduct it to the North Pole and the South Pole, protecting the rest of us from these particle storms. And over there, we have ionized activity in the outer atmosphere. These photons can interact with the atmosphere, the air molecules over there. And because of that, ionic activity takes place, right? You can have electrons jumping to higher shells and coming back and returning energy as light and so on. That is why we see all of these coronal displays. We see these aurora borealis in the north and aurora australis in the south and those kinds of things because of this activity. Now, the largest solar flare we have recorded so far is something called Carrington event in 1859. This resulted in such a heavily ionized atmosphere. Those days there are telegraph lines, no satellites, right? Telegraph lines. Telegraph lines are operated between Portland and Boston without turning on the battery power. Without even turning on the battery power, the lines had become so ionized that they could operate it like that. In other places, telegraph lines and even forests caught fire. That was the amount of coronal activity and sparking that was taking place. And coronal display, normally we see it in some small latitude, the northern North Pole, South Pole, but this was seen in latitude as far as Hawaii and China. This was a massive solar event. Nothing like this has happened since then on Earth. So this is the same thing I talked to you about. Billions of tons of this matter come and they impact the Earth and they conduct it over here and such things. Now, because of this activity in over here, when this radioactive activity happens in the upper atmosphere, they rain down on Earth. These particles rain down on the Earth and they're preserved in the ice in Antarctica as well as in the Arctic region. So that is what scientists do. They go and drill in Greenland or they go and drill in Antarctica, take these ice cores or like time capsules. They're able to sample this, calibrate it, and try to study the various isotopes over here, like beryllium and other such things. And they presented this paper. They're showing that these are the years before present, approximately in this particular time frame. They're showing all of these things are going out of the graph literally, right? They're shooting up all of these radionucleotide records in 9125 years event. So in other words, we had such a massive solar flare around this period of time. And what is the relevance of Surya's story? I don't know how big this event would have been. But Indians were definitely living in this area. They were living in the Saraswati Sindhu plain and other such things. They've observed something. Perhaps the atmosphere was so ionized that when you look up, maybe it's a haze-like thing. The sun appeared to be super bright, according to them. Super bright for a long period of time, right? Till Sanjana's father, Vishwakarma, comes and chips off sun's brilliance after a period of time, then sun resumes its normal size. That is what they say. So we are estimating that this Carrington event was logarithmically 10 times smaller than the 7176 BC event. It could have been observed as an increased brilliance of the sun for a period of time. Two studies are pegged to this time frame, tree rings and ice core records. We independently derived this from archaeoastronomy with Ashwini, the winter solstice, and got the same period. This is fantastic, guys. We got validation of something that is there in our texts with science. We got a validation addition. So this could be cultural memory that has been passed down for a long period of time till such time it was written down into the Puranas. Maybe in 3000 BC, maybe somewhere later. But the point is we have it in our Puranic records after that. That's how we're able to estimate some of these things. With that, we can rebut the Aryan invasion because so many instances of interest in astronomy is there in our ancient texts much before the alleged Aryan invasion. We can ask the question, how can Vedic concepts be in place in India prior to the so-called Aryan invasion of 1500 BCE? Max Muller, using linguistics, he said there's a Chandas period when the earliest books of Rig Veda, 1200 to 1000 BC, Mantra period, remaining books, Brahmana period, 800 to 600 BC, when the Aranyakas, Upanishads, Sutra period, when astronomy and other things are done in 200 BC. But then in astronomy, we have seen something else. Vedanga Jyoti is 1400 BC. Where is this and where is 200 BC? Brahmana, Shatapatha Brahmana, 3000 BC, Kritika, we saw that. But then Max Muller thought it as 800 BC. Clearly, we have a problem. Rig Vedic accounts of Aditi, Ashwini to this early time frame. But then he says Rig Veda was composed in 1200 BC. So we have big problems because we have things over here that don't correspond to what the linguistics is telling us. Well, Max Muller's approach to this was if you can't defend it, you discredit it. So he decided to discredit entire Indian astronomy. He wrote this book where he said that he doesn't trust anything in any Indian works. He said they're non-robust, and so he doesn't believe in any of those things. He only said he accepted Vedanga Jyotisha, that Colebrook, a fellow Westerner who said 1400 BC, that is after Aryan invasion. He said, okay, I accept that, nothing else. So he believed Aryan invasion. He believed the biblical creation date of 4004 BC. He believed in this. He rejected all the other facts and evidence as unreliable. So this is what we call confirmation bias, right? It's a failed methodology. Okay, so with that, we have come to the end of this episode where I've given you a glimpse of Indian antiquity and Indian calendar systems. I discussed Nirayana, Sayana notions and showed knowledge of precision. I discussed lunar and solar calendars and how they synchronize these things. I discussed a non-ideal celestial elements and how Indians are aware of these things. And I put a call out there saying that Indians have accommodated for elliptic nature of orbits by doing these things. We discussed the antiquity of Indian astronomy from the clues in the text and showed the great antiquity. So the next month, I might not be in the US, might be in India at that time, but if possible, I hold this episode, or perhaps we might do it the month following that, where we'll talk about coordinate systems and how Indians tracked planets. We'll talk about that. Okay, so that brings us to the end of this talk. If you like this talk, you may want to see some of my other lectures online. Go to YouTube, search for my name, you'll get a whole bunch of them. We can stop here and take some questions. Do we have any questions? Okay.
Looks like no questions for today. Typically, there's
Can I ask a question?
Yes.
Yes, please go ahead.
I always used to get amazed how our Indian and our ancestors in India, way back, made these almanacs, what we call Panchanga.
Right.
I've been seeing Panchanga for the last 100 years, or 200 years old Panchangas,
Right.
and some close astrologer friends of close relatives of mine who practice astrology. He said our astrology even was much earlier than the word astronomy was coined.
Right.
I don't know how far I am correct, but I am always amazed at your talk, the way you explain things, the way you narrated the years, which we have read in engineering also. Anyway,
Right.
very good talk,
Thank you.
Mr. Raj Vedam.
Thank
Excellent. I have been following you, and I had happened to see you once in Chennai sometime when I heard you talk someone a similar subject, and I am very sure you will turn non-believers to believers by this talk.
Thank you. Thank you so
Scientific
much.
believers.
Thank you. Thank you. Very kind words.
Probably. Thank
Yes.
you. Very
Thank
kind.
you. Thank you. Thank you. So only one point I'll make is we should reject the word astrology as it applies to Indian astronomy. We should only use the word Jyotisha. Jyotisha is the word that we
Very
use.
correct. Very correct.
We use Jyotisha Shastra, and that's what we should use because it's intricate astronomy, as I've been showing these last two lectures and the next two lectures to come. I'll show you more engineering fascination details of the scientific prowess of our ancestors in doing these things. So the Westerners chose to absorb everything, digest everything that we have in the mathematics part, and left us with things that they could not use. They could not use the predictive Phalita Jyotisha. Phalita Jyotisha is what we are using when we talk about predictions and things like that, which is a small component. Phalita Jyotisha uses the mathematics that we are talking about in order to do what it is doing. So this small part has been conflated to all of Indian astronomy, and people reject it, right? Because the Christian theology does not accept prediction. Thy will be done, God's will be done. So we cannot know the future. So they could not absorb Phalita Jyotisha. So they left us with that, calling it superstitious, backward, primitive, and these kinds of things. But this is the reality. In support of their narrative, they try to say that Aryabhatta copied from Ptolemy, we copied from Babylon, we copied from Egypt, and these things. And my talks have all focused on showing the utter bogus nature of those kind of narratives and showing this long citation trail that we have in India, where researcher after researcher is quoting the earlier one and saying, I learned from that person and this is what it is. Aryabhatta says, I learned everything from Brahma Siddhanta. There's a work called Brahma Siddhanta before him, which we don't have anyway, and by now it's lost to time. But he says, everything I've said here is in Brahma Siddhanta. That is much earlier than him. So where is Ptolemy come into the picture? So like this, we had to show with evidence, reject these Western assertions and show the reality of what our ancestors are able to accomplish.
Thank you very much, sir.
Thank you.
I feel very enlightened by your talk. And not that I can get enlightened by this 1 hour, 1.5 hours. I should follow all your older versions also of talk and will follow it regularly hereafter.
Thank you so
Thank
much.
you. Very kind of you. I am Gopalakrishnan from Chennai, now at present in USA. Thank you.
Wonderful. Nice to meet you, sir.
Thank you.
Any other questions?
Hello, Dr. Vedam. This is Aditya.
Yes, please. Aditya, go ahead. Oh, wonderful to see Aditya. Aditya is a professor in astronomy, for those who don't know, in Texas. He's a good friend of mine.
Thank you for another interesting talk. I would like to, so you did show all the simulations and all using Stellarium. How far we could go back in time and how much you could believe that? And of course, because people also talk about planetary positions and all.
Right.
So how much you can reliable?
Thank you for that excellent question, because that is what engineers need to talk about, scientists and engineers. What are we using as data? We are trying to use a pramana of Stellarium, which is planetarium software. What is behind that? Planetarium uses a package called VSOP 87, which is a numerical package it is using. If we have to compute celestial body positions, we must in reality use n-body dynamical motion, which is exceedingly difficult to do. So what we do is we have polynomial approximations for the planetary movements. With polynomial approximations, we are able to work backwards in time and so on. But physics tells us that planetary orbits are chaotic. Because of their mutual center of gravity, you can have tugs, right? When 2-3 planets come at the same side, you can have an excessive tug on one side, less on the other side. So slight tugs. We cannot estimate whether it's just in meters or kilometers, but there are changes in these things. So over time, these little differences can become quite big in orbital terms. So we know planetary positions are chaotic, or rather orbits are chaotic. We know that the software that we are using is based on polynomial approximations and not dynamical simulation, integration, in other words. They're not doing integration. So the questions come, what are the errors? What are the errors in these things? So two sources of errors. One source of error is when a polynomial is pushed beyond the planned boundaries. When we do interpolation, we are okay. When we do extrapolation from beyond the planned interval, errors build up. And that's what happens in these things. So question comes, what is the accuracy limit of planetary position estimation? Well, the developers of the software itself say, don't use it for too much, maybe not beyond plus minus 5,000 years or even less, even maybe 2,000 years or so on. Beyond that, the planetary positions are in doubt. So I never use Stellarium or any software to determine where was Mars 5,000 years ago. Utter nonsense. We can't do that. We can't do that because that kind of accuracy is impossible to get. But what are we doing? We are saying what was a nakshatra at vernal equinox point? What was the nakshatra at winter solstice point? That is far more robust because the stars in relation to our solar system, they also have a proper motion. They are also going around the galactic center. But then that movement is not as pronounced as a planet's movement. So the approximation of those things has got plus minus 10,000 year accuracy.
Okay.
The approximation.
But that
Yes.
gives an opportunity for us to go from polynomial approximations to the integration methods. If one could develop that, that can be a marvelous.
Exceedingly complex. Exceedingly
Yeah, true.
complex. Yes.
But if we could do that, that will be a project in itself.
Yes, yes, indeed, indeed, indeed. So the unknowns, there are many unknowns, unfortunately. When we start developing a model, the unknowns are tremendous. Even our estimation of the planet weights and so on, even that can have an impact. Right now, we're estimating planet weights based upon Kepler's laws and things of this nature. But even that can, the errors in that can build up over time. So we have to be super careful in whether we integrate it or use polynomials. We should know accuracy is limited and we should be cautious. So all the studies I've done so far are with respect to nakshatra positions, far more robust than saying where was a planet 500 years ago, 5,000 years ago. We are not doing that. We are saying where was a nakshatra 5,000 years ago, 10,000 years ago. That is much, much, much more robust.
So for the
That's why
for the planets, you will ask us to go till 2000 years.
I wouldn't even say 2,000 years. I'd say perhaps even less than that. I would say maybe hand waving. I'd say 2,000 years. So, but it could be even more limited.
Okay, good to know that, because people do all those and then they come up with some
Yes,
numbers and figures. So it's, I don't know how much to believe those then.
yes, yes.
Okay, great. Thank you. Thanks for
Thank you.
interesting talk. Thank you very much.
Thank you, Aditya ji. So, Sundari, please go ahead. Hand is raised. Sundari ji, please go ahead.
Namaste.
Namaste.
Most enlightening talk. I listened to your recorded portion also at least 2-3 times
Oh, thank
to
you.
grasp fully, because I'm a student of the Shastras only. And one thing that is really, when people ask me, not me, this English word astrology and astronomy and every paper, the prediction, Jyotisha.
Huh.
Jyotisha is the science of the planets and
Yes.
cosmic bodies.
Yes.
And how is it, when did this India, I keep on searching myself, when did this predictory things came that if you are born in this star, it's neither in the Surya Siddhanta nor in any of these books that I'm
Right.
trying to study. You can throw a little light so that
Sure.
people having this misguided idea of predicting, if you're born on this will happen, and it keeps on changing. How did the people who wrote the books that your son will become a software engineer if he's born on this star?
And those are modern
Recently,
predictions.
I have condemned that idea of one of the astrologers.
So,
Please, a little light on it if you
Sure,
can
sure,
throw,
sure.
maybe in another talk.
I'll very quickly summarize a little bit about this. So, Phalita Jyotisha came about in works, for example, by the Rishi Bhrigu. Bhrigu himself, at a very ancient period of time, has talked about these things. Then, in our recorded works from Varahamihira wrote Brihad Jataka, Brihad Samhita, Brihad Jataka, from those works, and Rishi Parashara has written about these things. Several rishis have written about these things. So, the way that we should take it is, our ancestors were brilliant people. They applied everything possible. Today, as an engineer, what do? If I want to, let us say, control something, I first construct a mathematical model of that object. To construct the mathematical object, I must know the physics, or empirically I should know how it's behaving. And I write down those things. I take some measurements. I figure out what the parameters are for that model. Then I use that model in some sense. Once I validate a model, I use it for prediction. I'll predict how will that model behave, like a what if kind of analysis. What if I make the force so much, the pressure so much, voltage so much, current so much. So I don't have to test it on the actual system if I have a model. So what if kind of prediction is an accepted part of today's technological world, where we use predictions in order to make decisions. We use predictions out of validated models in order to make decisions, whether it's on corporate decisions or technological decisions or econometric decisions. We do this all the time. Our ancestors are pioneers in this. They were trying to see what is our karma phala. How will my karma phala bear out? To give some empirical ideas over here, supposing a child is born in ancient India, let us say a child is born in, let us say, when the harvest is done. When the harvest is done, there's a lot of food in the village. Mother gets good nutrition, child gets good nutrition, health is good, and so on. Supposing the child is born, let's say in winter time or a time of drought and things of this nature, when food is not there or things like that. Now the child's health is also impacted. Our ancestors have observed cycles in everything, whether cycles in seasons, cycles in astronomical events and celestial bodies, cycles in human behavior, cycles in biological beings. Everything they've seen cycles. So they also saw how they could map the karma phala of somebody, the philosophy of the land, in terms of the celestial cycles that they were seeing. So they have made some empirical models over there that talk about good periods and bad periods based upon these things, based upon basically a person's birth chart or things of this nature. So one has got to be very careful in dismissing things. Just as we are careful in accepting things, we should not just dismiss it only because you see some practitioners who are talking nonsense. We have to go deeper into our own history to see where did these things start, why did they do these things, how did they apply it, what was the utility for that, and we learn a lot from these things. But I give you a modern analog. We use prediction in a certain way. Prediction is used in today's technological world in a certain way. So there is no question of throwing away its utility. One has just got to see the validity of these studies and why they were applied. Okay, hope that addresses partly.
Thank you very much. So we should go to the original books and not these practitioners misguiding. There are some practitioners who are actually very knowledgeable, but there are some commercialized misutilization taking place. No, that's what.
We also have to be careful that there's a lot of bad press as far as Indian sciences are concerned. The Westerners could not accept predictive part because, like I said, theologically it is against what they believe in. Similarly with the Islamic people, though Islamic people borrowed some of these things, they too had a theological something against prediction and things of this nature. The modern press completely is against anything like this, saying it's primitive, backward, superstitious. There's in popular media, movies, there's always an attempt to mock the Indian practitioner of these things. So we have a tendency to do this, but we have to be careful. Just like there are good scientists, there are bad scientists, there are good engineers, there are bad engineers. So like this, you have to take that, yes, there are good scholars and there are bad scholars who understand some of these things. So a good scholar would understand, for example, precision, they'll understand all the cycles happening over there, understand how the model should be changed. And we have evidence of these things. We got something called bija corrections, which Bhaskaracharya and others have done to correct for precision, correct for various other things. So such evidence is there that Indians have observed, made corrections based upon observed phenomena, keeping track of the scientific notions out there and such things. So bottom line, be careful. Don't outright reject. Neither.
Which is the main book for this Phalita Jyotisha that people refer as?
You can. I'm not sure. I'm not an expert over there. I've not studied this.
Maybe if you get, please post it.
Start with
people
Varamira.
Asking me about it and I'm not able to answer. That's why.
Start with Varamira.
Main consultant.
Varamira and Parashara Samhita. Take those two things and.
Thank you very much. Thank you very much.
Okay. Any more questions?
You mentioned, sir, that some superstition is being linked to this subject by some people. Is it because this Chaturayuga, Kalpa and other things, are we link it to Brahma and Vishnu and all? Can it be because of that?
I think it is more theological resistance to this. When the telescope was discovered in Netherlands and later used by Galileo, this whole business of modern astronomy was born from there, observational modern astronomy. They wanted to put some distance between what they were doing and their own ancestors are following astral methods. Their own ancestors, meaning European ancestors, even Newton and others were following some of these things prior to this Galileo's time. So they wanted to put distance between that and what they were doing here. And in order to put that distance, everything was discredited. So the whole business of superstition came through a number of reasons, and one of them was to show that they are progressive, modern, technologically advanced, because this is a time when the Renaissance period was also happening, the Reformation, and also these ideas of modern. Modern means moderna, which means now, as opposed to then. right? Technologically advanced as opposed to primitive methods. So these are the kind of ideas that came in Europe around 1500, 1600s and so on. And that shows in the way they treat some of these subjects.
But most of these have been documented in our Bhagavata Purana.
Yes.
This
Many
Satu
books.
Yuga and Kalpa and
Yes.
4.32, all those
Million
things
years, yes.
you enlightened us. Thank you very much, sir. Very kind.
Thank you, sir.
Thank you.
I think, Trisha, the no more questions. We can close the talk for today.
Yes, sounds good. Thank you so much, Dr. Vedam, for this incredible talk. Looking forward to the next one, and you'll all receive emails about that for registering. Thank you.
Wonderful. Thank you. Thank you, everybody. Thanks for your patronage. Bye. Good night.